once again, welcome. This is going to be not a full hour. I think what I'd like to do with these sessions is to give you a bit of a shorter, like the 25-minute, half an hour introduction to some areas of maths and physics which you will come across, possibly beyond A level in truth, but which are accessible to you now with a little bit of help. So I'm going to start this session by describing something you already know. So without further ado, you're going to think, wow, this is easy. So this is what you call an equation because it has an equal sign in it, right? And the solution to this equation, if you solve this, I could go into detail about how to solve it, ultimately you're going to get x is minus what? Sorry, what am I even? Minus 2. Minus 1. Yeah, right? One all said and done. So, oh, hang on a minute. I'm having an email from Mr. Hingston. This is going to ruin my recording. No, that's fine. Sorry, Mr. Hingston, if you're watching this recording. So the equation has a solution which is a number. So this is a number. Similarly, there are more complicated equations, right? X squared minus 1 equals 0. That also gives you two solutions because it's quadratic, which are numbers. X equals plus or minus 1. Fine. So there's this thing called an equation which gives us solutions which are numbers. So what I want to talk about today is not normal equations, and I've already told you what this session's about. It's called a set of equations which are known as differential equations, and you come across them a lot in physics and in chemistry, and for that matter, you can come across them in biology or economics or meteorology, because a differential equation is an equation which involves derivatives. And to remind you, a derivative, dy by dx, is the archetypal derivative if you're a maths A-level student. It tells you something about how one quantity changes with another. So in any situation where you've got a change with time often, but also with other quantities, so things like a changing position or a changing magnetic field or a changing number of people infected with a virus or a changing population of predators within an ecosystem or a changing demand for a item on the markets or something, you can talk about derivatives. For the record, they're different from, there's another kind of derivative when you talk about finance, which isn't related to this. So we're talking about mathematical derivatives. So let me write a differential equation for you. Oh, sorry, no. Let me write this one. dy by dx equals 2x. The reason it's called a differential equation is that it's got this bit in it, dy by dx. Now, the solution to this differential equation is not a number, it is a function. We're asking the question, what function, the function y. What function y of x satisfies this equation? Now, if you've done maths, you can maybe see that by inspection. It's x squared. Because if you differentiate y equals x squared, you get 2x. Okay? So that's a very easy one because you can almost see that from basic A-level maths, what the solution must be. In fact, it's not only y equals x squared. In fact, the general solution would be y equals x squared plus c, because the constant differentiates to 0. Okay, so that's the general solution. How do you solve this? Now, this one is easy to solve because you just do a process called separation of variables. So I'll show you that. What you do is you bring the dx up to this side and then integrate. And of course that gives you y on that side, and then differentiate 2x, you get x squared, and then of course plus c because it's a indefinite integral. Now, I know exactly what you're thinking, you know. You're thinking, isn't that just integration? Well, yes, but remember when I said this is a simple differential equation. So this is a simple differential equation, and this method is called just the separation of variables, because what we've done is we've separated the dy and the dx. Okay, we've sort of treated the derivative a bit like a fraction. So that's one type of differential equation. What's important about differential equations is that the solutions are no longer numbers, they are functions. So you don't get roots of a differential equation, you get functions out of a differential equation. Next, what are differential equations? What kinds of differential equation can you get? Well, let me write a few down. Just to give you an idea of what they might look like. So that's one example. Another example might be dy by dx all cubed plus d3y by dx cubed. I mean, this would be nightmarish. Equals cos x. Okay, so those are two more complicated differential equations, and they're more complicated because this one involves a second derivative, and that means it's called a second order differential equation. And this one on the right hand side is more complicated because it has a third derivative, so it's third order, and it has a power of a derivative. It's dy by dx all cubed. So it's also non-linear. Whereas this one here, you describe as linear because there are no powers of derivatives, or x, or y for that matter. So that gives you some idea of how you might classify differential equations. Obviously, these only involve y's and x's. You can have differential equations which have y's, x's, z's, t's, multiple variables. Now, I'm going to limit our discussion to physics. Okay, so in physics, particularly when you're starting out, even at low, sort of basic level of university, you don't go beyond this type, this second order differential equation. What I'm going to do for this bit is write a few differential equations down from physics and tell you where they come from and what type of physics area they're from. So, and some of them you might recognize. So physics examples are m times d2x by dt squared equals F, or sigma F, let's say. So that's one rather famous differential equation. So that's number one. Number two, well, let's go with dn by dt equals minus lambda, which is a constant, times by n. That's another differential equation which is related to an A-level topic. And the third one, in fact, let's do the third one over here. So the third one, what shall I go with this time? Oh, I'll go with this one, which is one that we've discussed before. All right, the Schrodinger equation. Okay, so those are three differential equations which you come across in physics. There are loads more, but those are three ones that spring to mind. So what are these? You might like to just have a think to yourself for a minute. I've already told you what this one is. This is old Schrodinger's equation, which I actually did a session on. This one on the left here is nothing other than F equals ma, because acceleration is just the second derivative of the displacement with respect to time. So this is Newton's second law. And the middle one, this is the number of radioactive nuclei in a sample. N is the number of radioactive nuclei in a sample. So this equation tells us how the number of radioactive nuclei changes with time during a decay, basically. So this is the radioactive decay law. Now, if you're in the first year, you will study this middle one as part of nuclear physics. And hopefully in the first year, you've come across already Newton's second law, right? So that's definitely something you've come across. You've just not written it in its full mathematical form. Okay. So this should illustrate that this sort of type of mathematical equation, one involving derivatives and things where you are considering the change of one thing as another thing changes, that's like the bread and butter of science, isn't it? Right? Reaction rate changes with temperature. Force causes motion to change. The number of radioactive nuclei changes with time, right? The universe is a dynamic place. The size of a star changes with time or temperature, right? So that's why these are so important. Next, so this is part 4, I suppose. I'm going to take Newton's second law and show you a particular kind of motion, which is going to be a revision for Andrew, basically the second year. So I'm going to rewrite Newton's second law down here. So I'm writing mass times acceleration equals force. And I want to consider this situation. I'm going to have a spring with a mass hanging from it. In fact, a spring with a mass hanging from it. Or maybe, can I change that? I'm going to have a spring, horizontal spring, and it's going to oscillate back and forward. So let's put a mass on the end of it. Now, what you should remember, or you might have come across, is that if you extend a spring by a distance x, if you extend a spring by a distance x, if it obeys Hooke's law, then the restoring force is going to equal kx. So that's Hooke's law. So if you think, well, if I displace the spring, the mass on the spring to the right, the restoring force, the force that it feels, is back towards where it came from, right? Back towards the equilibrium position. If you stretch a spring, it wants to pull you back to the original position. So the Newton's second law becomes m d2x by dt squared, and instead of f, we put minus kx, because this minus sign tells you, or comes from the fact that this force is in the opposite direction to the displacement. You pull the spring to the right, the force you experience is to the left. If you push the spring in, so if you compress the spring, so you pushed it to the left, the force would be to the right. Okay, so this minus sign just shows that the force is in the opposite direction to the displacement. Don't worry too much about that. You will cover this type of motion in the second year. Anyway, what's the point of that? Well, it means that our differential equation ends up becoming this. Now, we can solve this. We can solve this. Because, let's rearrange it, shall we? d2x by dt squared equals minus k over m times x. Let's bring the k over m to the other side, so plus k over m times by x equals 0. So can you see that this is similar to one of the equations we had up here? This has got a second derivative in it. And you see this second order here, this one. The one with the second order, the second derivative in it, it's called a second order differential equation. So it's actually one of these that we're looking at, Newton's second law. Now, if I said, those of you who thought, God, that was easy, when I did this one here, remember this one, which was just x squared plus c, you were probably thinking, God, I could do that. I can integrate 2x. But what about this one? It's not so simple, is it? Because you can't, you can't really square root a derivative, right? It doesn't really work. Now, there is a way of solving this, which I will talk about at the end. But what if you were to guess a solution, right? Let's just guess. This is a legitimate strategy sometimes. Guess. Often you'll hear this called an ansatz, which is, I think it's German for, well, I don't know. It's a German word anyway. It means a kind of a guess, a hypothesis. So let's guess the solution is x equals a sine x, right? We've guessed that. Oh, sorry. Can I make a substitution here? I'm going to, instead of k over m, I'm going to write omega squared, just because. Well, just because. So let omega squared equals k over m. Right. I'm going to suggest the solution, a sine omega t. So this is my guess. How could I prove? Is there a way I could prove that that's a solution to this equation? I'm not expecting you to necessarily know. The way you'd prove it is by substituting You know how if I wanted to prove that what -1, this -1 was a solution to this, I would just substitute the value -1 in for x. Well, we can do a similar thing here. What if I differentiate this dx by dt? Oh, your first year, so you won't know. I'll tell you, to differentiate sine, you have to use the chain rule. So you differentiate what's in here to get omega, then multiply it by a cos omega t. So sine goes to cos if you differentiate. If you differentiate that again to get d2x by dt squared, you do the same thing. You differentiate the omega t, so you get an omega squared out the front, another omega. The a stays as it is, it's a constant, and then that becomes minus sine. So if we now, so in other words, this down here is what you get if you differentiate a sine omega t twice. Now let's substitute this into this equation. So d2x, we've got d2x by dt squared plus omega squared x equals 0. If I substitute in this here for the first term, I get minus omega squared a sine omega t. If I substitute x in here for a sine omega t, I get plus omega squared, from this omega squared stays where it is, multiplied by a sine omega t. So this is that x, and this minus omega squared a sine omega t is this here. I've just substituted in those two things. And guess what? Are both sides equal to each other? Well, these two terms, minus omega squared a sine omega t and omega squared a sine omega t, are the same, aren't they? And we've got minus something plus the something. So this equals 0, which of course balances with the right-hand side. So we're good. This tells us, therefore, x equals a sine omega t is a valid solution to the differential equation. Right? So we've proved it by guessing and then proving that it satisfies the equation. What does this look like? Well, if we remember x is displacement, what does a sine graph look like? Well, it looks like this. And so this suggests that the motion, if you pull a spring downwards or to the side and then let it go, so we pull this spring to the right-hand side and then let it release it, it suggests that the motion of it, if we're not including friction, remember, so this surface here that I've got this resting on is frictionless. So in the absence of friction and air resistance, you'd get an oscillation, sine wave, right? You'd get positive displacement through the equilibrium back to negative, and that would repeat. So this is an example of oscillatory motion. So this has actually got a name. It's called simple harmonic motion. It's the most simple type of oscillation that you can imagine. Okay, sinusoidal. But where did this come from? Well, really, it came from this. So the Newton's second law, d2x by dt squared equals minus k over mx. Remember that we put, that's what we started with, F equals ma, with minus kx being the force. If we follow through with the maths, what comes out? Trigonometric, sinusoidal, oscillating motion. Now, I guessed that, didn't I? This was a guess. remember, because I know what the solution is already, and I showed you that it is the solution. You might be wondering, how would you solve that if I didn't know what the solution was? So if I had the same equation, how do you solve this? Now, what I just did, this stuff down here, that's second year A-level maths, right? Trigonometric functions, differentiating them, blah, 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 blah. This bit, plotting a sine function, is just first year. This is further maths, and at that, second year further maths. But I'm going to give you an idea anyway, even if you don't understand it at all. So there is a function called the exponential function, which is e to the, I'm going to write e to the lambda x. Oh, I've changed that, haven't I? Let's make this y, instead of y and x, make it x and t. So it's x and time. So there is a function called the exponential function, which is e to the power something. Hope you might have come across that actually, this idea of exponential growth and exponential decay. If we substitute this, so look what we get. If we differentiate this, you get a lambda e to the lambda t, because remember the lambda, I say remember like you've done this, but even if you've not done it, you just have to take it from me. That's what you get. If you differentiate that again, you get another lambda coming down. So a lambda squared e to the lambda t. If you substitute, you see I've got d2x by dt squared, and I've got d2x by dt squared, and I've got x, and I've got x. So look what happens if I substitute those in. I get a lambda squared e to the lambda t plus omega squared e to the lambda, a e to the lambda t. So I've just substituted in these expressions, these bits, to rewrite the equation. You can see something happening here, because you've got a 0 on this side, so you can cross the a off, and you can cross the e lambda t off. So you've got lambda squared plus omega squared equals 0. So for any second order differential equation, what you do is you start from this function, a e to the lambda t. You just do, right? It just so happens that whatever second order differential equation you have, you will always get some kind of quadratic involving this lambda here, right? Now, this is quadratic equation. Remember, omega squared is just a constant involving, I think in our problem it involved K and M, the spring constant and the mass. Don't worry, I'm almost finished. I'm not going to go on for too much longer. This is, you can treat this, guys, as a sort of sneak peek into something which you're eventually going to be able to understand and do yourself, but not for a little while. So this, if you solve this, look at what you get. Lambda squared equals minus omega squared. So the solutions to this are the square root of minus omega squared. Now, up until now, you have not come across complex numbers, but in order to solve this equation, you need to use complex numbers, because the square root of minus omega is actually omega times the square root of plus or minus omega times the square root of minus 1. Now, you might have read about this yourself, and your maths teachers might have mentioned it, but the square root of minus 1 is a number, it's an imaginary number, and we give it a symbol. It's given the symbol I. So in fact, the solutions to this equation are, why is Finn entering this now? Right. What? Anyway, lambda equals plus or minus I omega. Now, and by the way, that means that the general solution to this equation is a e to the omega t, because we've got one lambda which is omega, I omega, and one which is plus minus I omega. So one is e to the I omega t, and you have to just add the other, and you can do this because it's a linear equation, so you can superpose solutions. So a superposition of general solutions is also a solution. So these are solutions separately to my differential equation, but because it's a linear equation, right, because it's linear, oh damn, you can take all the separate solutions, add them together, and that will also be a solution. That is called the principle of superposition, that you already know, actually, because it's similar to what you get for waves, right? If you have, individual solutions or individual waves passing through a region, you add them up, and that is also a legitimate solution. It's slightly different, but it's still called the principle of superposition. Now, this thing ends up being, you can write it as this, and I'm not going to explain why, I'm sorry. But these two are the same, which is mind-blowing when you first come across it, because what I've just demonstrated to you is twofold in its awesomeness. One element is that in order to solve Newton's second law, this thing, for an oscillating mass, you need to use complex numbers. That's number one awesomeness, right? You need complex numbers to solve an oscillating mass with Newton's second law. Number two is that there's a relationship between complex exponentials involving complex numbers and sine and cosine functions. Now, you might not have come across complex numbers before, but I've just said, I'll repeat it, that complex numbers are, there's a vital link between complex numbers and trigonometric functions, and complex numbers and solving simple physics problems. Now, if that didn't convince you of the reality and importance of complex numbers, then nothing will. So remember that next time someone says to you, oh, the square root of -1, it doesn't exist. Now, that's just a little window onto how calculus and some of the maths that you have done and have yet to do enter into the study of physics. It's 4:34. That's all I'm going to say for now. I implore you to go and find out about this stuff yourself. Go and do a bit of reading. Ask Dr. Page or Dr. Marshall, whoever you have for maths, if you want to know more, because there comes a point at which they're far more qualified to talk about pure mathematics than I am. So I hope that's been useful. I'm going to sign off there. Thank you very much.
Thank you, sir.
Okay.
Thank you, sir.
Finn, you're a bit early. I was literally just finishing my I was doing further physics for the specialists, and you do realize it's at 5 o'clock, yeah?
Yes, sir. I was just queuing it so that I wouldn't miss anything.
Fine.
Sorry.
Okay. Well, I'll start at 5, but I'm just going to mute myself. Oh well. I wasn't. Well, we'll just wait, shall we?
Yeah, sure.
So I'm going to